Okay, so one of the questions that came up during the last lecture was this question of, okay, what are we doing with these models besides clustering? And so that's one of the things we're going to answer this time. I'll start off by saying there are a lot of different types of data structures that we can look at. So a couple that Mike sort of mentioned already are not just clustering, but cases where we have a collection of different maybe data corpuses of documents, or in general different data sets, and we want to share power across them. Another situation that we mentioned earlier, but we didn't go into much depth in, is where you might have some sort of tree information. So for instance, in genetics, you might want to construct a tree. You might actually even want to construct, sometimes even more than a tree, you might want to be able to sort of coagulate and fragment the sort of branches in your tree-like structure. And here I'll be talking a little bit more about graphs. So by the way, let me just mention, if you're interested in particular in the code, because eventually all of this will be up in video and is being recorded, but if you're interested in the code, it's at my website from part 1, and I'll just be putting my slides up there as well. Okay, so what I'll be talking about in this case is networks and models over networks. And of course, there's tons of data nowadays that's network data. And not only are we getting more and more network data sets, just like we're getting more and more of any other type of data sets, but in fact, those networks are growing. So we're seeing more and more people join Facebook, more and more people send emails to each other, and so on. And so we want to actually have models that can learn in those growing networks. And we want probabilistic models and Bayesian modeling for the same reason that we've wanted it this whole time for other types of data. So we might want to capture rich relationships in data. And here I don't just mean relationships between nodes in the form of edges. I mean that we might actually have different graphs, and we want to capture that there's some shared parameter between those graphs and maybe share information that way. Or we might want to capture that different parts of a graph are connected by some shared latent parameter. We might want to capture communities in graphs or different relationships among links. If we have parameters, often one of the reasons that we're being Bayesian or taking this kind of approach is that we want to get uncertainties. We want to get coherent uncertainties across our parameters. And of course, if we have any prior information, perhaps of some sort of physical process or something like that, we might want to incorporate it as well. Okay, so this isn't a new idea. There are tons of models out there. I'm mentioning a super small handful right here, but I can't emphasize enough that there are so many more models that I have not listed on this page. So there was this really nice overview by Lloyd et al. in 2012, and they go over a number of models. I'm sure there are tons more that aren't even in there, but there are just a lot of probabilistic models for networks that are out there. Now, one of the things that we might ask is, how do these models capture streaming data? So that's certainly one of the things that we've used, especially from the first lecture, in motivating Bayesian nonparametrics, right? So you think back to what we were talking about with clustering. We imagine that we have more and more data points, and we don't want to limit ourselves in the number of clusters. In fact, we want the number of clusters to be able to grow. And so we can think about the same thing here. We imagine that we're getting more and more data, creating these graphs, and we want to say, are we capturing the right growth properties in those graphs? Just like in clusters, we said, sometimes we need to go to the Pitman-Ure instead of the Dirichlet process because we want to get these power laws and maybe the growth of the number of clusters as a function of the number of data points. Are we getting the right growth properties in graphs? Okay, so one really simple property that is much more simple than anything we've talked about in terms of growth is the following property, projectivity. So imagine I'm studying some set of emails between people. And they're all emailing each other. Maybe they're all in a company. And we imagine that because somebody sent an email 2 weeks from now, that shouldn't delete an email that I see today. Of course, I should just be accumulating more and more emails in this scenario. Nothing should change about the past. And so if I make this assumption, this projectivity assumption, that this future data doesn't change anything about the past, then it turns out all of these models and many more very popular models that people are using are misspecified, in the sense that they generate dense graphs, graphs with too many edges, in a way that I'll make precise shortly. And so we might want to come up with a model that doesn't do this. That doesn't generate these dense graphs with probability 1, these too many edges with probability 1. And so I'll be talking about a new framework for sparse graphs that we've been working on. So in work that we've done recently with awesome student Diana Kai and my great postdoc Trevor Campbell. So both of them have been first authors on some of this work. We come up with a new framework that lets us get sparse graphs. And this is one of these sort of Bayesian nonparametric frameworks. Yeah.
So what is the problem with the stochastic block model?
Right, so the problem, and I'll go into this in more detail in just a second to explain it more, but the problem is fundamentally that if we imagine that this is a growing graph, so we're getting more and more nodes and edges, then the number of edges as a function of the number of nodes is sort of too many edges. Again, in a way that I'll make precise shortly, it turns out it's basically quadratic, and there are a lot of graphs, a lot of sort of real life graphs where we seem to not see this. And so we'd like to have models where we don't necessarily have this quadratic growth as an option. Yeah?
There are also models like differential attachment, which are sparse. So where do they?
So we'd like to have Bayesian models that have this option. So let's come from the perspective, just for the moment, that supposing we're interested in this Bayesian framework, can we come up with models that allow us to have this sparsity property? But yes, there are definitely other things that one can do that would generate sparse graphs. Yeah. OK, so I'll talk a little bit more about this model misspecification. I'll define exactly what a dense graph is, and a sparse graph for that matter, and this new framework. And along the way, we're going to come back, even though this seems like quite a different problem, we're going to come back to clustering. And we're going to see that it actually relates to this and lets us get some nice characterization theorems. And in fact, we'll learn more about clustering along the way as well. And let me just mention, so I'll be talking about some work that we've been doing in graphs quite recently. And actually, there's been some awesome concurrent work by another group of researchers, Crane and Dempsey, and I'll encourage you to check that out as well. OK, so what is the problem with graphs? Let's get into this a little bit more deeply. So here, we're not just looking at a single graph, a collection of nodes and edges. We're actually looking at a sequence of graphs. So we're thinking, OK, at any point in our sequence, we have a graph. It's a collection of nodes and edges. And then at each step going forward in that sequence, we imagine that we add some nodes, we add some edges, maybe we add some nodes and edges, or we don't do any of these. But we never subtract anything for the moment. OK, so here we're adding a node. Here we're adding some nodes and an edge. Here we're adding some edges. And we imagine that the sequence goes off and has a countable infinity of steps. So this is just like in when we were talking about the Dirichlet process. We imagined that we had a data point, and then we added a second data point, and a third data point, and we just went off to infinity. OK, so when we have this sequence of graphs, we can imagine that a particularly interesting case is the case where the number of nodes goes to infinity in this sequence. And so if that's the case, then we can define a dense graph sequence. So here, density is actually a property of a graph sequence rather than a particular graph for this particular definition. We can define a dense graph sequence as a sequence where the number of edges grows quadratically in the number of nodes. OK, so what's problematic about quadratic growth? Well, not necessarily anything. But if you think about it, if you have all of your edges, if you have all of your nodes, and all of them connect to all of the other nodes via edges, I have a complete graph, then I'm going to have quadratic growth. I'll have number of edges equal to number of nodes choose 2. And so somehow this is like saying, we have some fraction of a complete graph, which is probably too many edges for at least some applications. And so what we'd like is to not have that. And that's all that this line is saying, that we'll say we have a sparse graph sequence if we have strict subquadratic growth in the number of edges as a function of number of nodes. So in real life, you probably want something much stronger than this. You want some strict power law, or some power law strictly less than 2. You want maybe n log n growth, or even linear growth. But for here, let's just define sparsity this way. And what we're going to do is we're going to find that, in fact, all of those graph models that we saw earlier can't even satisfy this. OK, so what is this problematic?
You want to be connected?
So, well, there's a difference between connectivity and density. So these are different questions that you might ask. For the moment, let's not be too concerned about connectivity. Let's just imagine that we have a general graph that we're not necessarily constraining to be connected. And in some sense, I'm defining a framework in the way that Mike's been defining a framework in the past 2 lectures. Here's a broad set of models that we could work in, and then we start thinking about specific models. But connectivity, I think, in either of these cases would be a little bit difficult, and perhaps we can revisit that question at the end and to see why that is, or at least as a constraint. Yeah?
Is there any connection to graph limits and graph form?
Yes, there absolutely is, and we're going to see it basically in a couple of slides. OK, so what's this problematic framework where we're getting dense graphs? So let's imagine the same thing we were doing before. We're getting a sequence of graphs, but now we're adding exactly one node at each step. So here, on the first step, we have one node. And since we're adding one node at each step, we can label that node by the step on which it's added. So the first node comes in on the first step. The second node comes in on the second step. The third node comes in on the third step, and so on. And the way that we're getting edges is we say that whenever a node comes down, it connects to all of the previous nodes, the existing nodes that we've already seen, if it's ever going to connect to them. So at this point, we know that node 3 and node 2 are never going to have an edge between each other. And we just keep doing this off to infinity. And again, we're thinking in this case about these probabilistic models, these Bayesian models. And so if we think of, imagine that I have some model, some distribution over this graph sequence. What are properties that that distribution might have? Well, a natural property that we've been talking about basically, for much of the last 2 lectures at least, is exchangeability. That's something that really motivates a lot of this Bayesian work, is being able to say that, I can permute 2 of my data points and nothing changes about my distribution. But here, I don't really have data points so much. So what is the thing that I could exchange? Well, something that might be natural is to think of the nodes. Maybe these nodes are people who are joining Facebook, and I think, I don't know too much about all of these different people. They're joining Facebook. I think maybe I could have seen them in some different order, and it shouldn't change anything about my distribution. So this is going to be the idea of exchangeability or graph exchangeability, that I could take any step out of this sequence, and I don't think that the probability should change if I happen to see the nodes in a different order, if I happen to label them in a different order. OK, so Aldous and Hoover, around 1980, were studying this form of exchangeability. It's an old idea. And the one tweak that I'm going to make here is I'm going to call it node exchangeability to emphasize that the thing we're exchanging are these node labels. OK, so we've seen a way to generate a lot of cool exchangeable distributions for clustering today. Let's talk about how we might generate an exchangeable distribution for graphs. OK, so what we're going to do here is we're going to have the unit interval from 0 to 1, and in fact, the unit square. So we have the x-axis and the y-axis, and we're going to put down some function on this unit square. I'm going to call it w. It takes x and y as its arguments. It could be some random function, so this could just be some realization of it. It could be a super complex function. So here I've drawn whatever was easiest for me to draw. So maybe it has high values here and low values here, but this could be coming from some Gaussian process. So long as I squish it so that the values are between 0 and 1, because we're going to interpret its values as probabilities. So every w value has to be between 0 and 1. OK, and it's symmetric about x equals y, and so I just drew it up here. Now, the way that we're going to generate a graph from this is we're going to say, for every node, we're going to put down a uniform random variable between 0 and 1, independent from the potentially random w. And we'll just keep doing this, IID for each of the nodes. And we'll say that the intersection of these 2 values is the potential edge between these 2 nodes. And the probability of this edge is equal to w at that intersection. And so we flip our Bernoulli coin with probability equal to w at that intersection. And maybe in this case, we just happen to get an edge. So we put that edge in. Now we do this again for the third node. We're going to put down our IID uniform random variable for this node. We are going to look at the intersection here. In fact, there's 2 now because there are 2 potential edges. We're going to make conditionally independent Bernoulli draws at each of those with probability equal to w. And that's how we're going to decide, maybe in this case, we happen to not get edges. OK, so we keep doing this. We make these IID draws off into infinity. And I think what's straightforward to see is that this generates a node exchangeable graph. Because if I permute any 2 of these IID uniform random variables, I'm definitely not changing the distribution of the graph. And on the other hand, each of these IID uniform random variables corresponds to a node. The awesome thing, and the much harder direction, is Aldous and Hoover showed in around 1980 that every node exchangeable graph can be expressed in this way, or the distribution of any node exchangeable graph can be expressed in this way. And so this is the graphon connection that was asked about earlier. So if I have any node exchangeable graph, I can come up with some function w, and I can make these draws, and I'm going to get back the same distribution over graphs. OK, so why is this important to this density question that we talked about earlier? Well, let's look at the expected number of edges in this graph, maybe the nth graph. Okay, well, there's n choose 2 possible edges, where n is the number of vertices, because it's just the same as the number of steps. W is the probability of the edge, and then we integrate over the 2 uniform random variables. And we take an expectation because W might be random. Well, n choose 2 comes out, and it behaves asymptotically like n squared. So here the squiggle notation is just for asymptotic equivalence. And then the rest of this is just an expectation over something that doesn't involve n. So it's got a constant. It's basically a constant. And so remembering that n is just the number of nodes, we see that the number of edges and expected value is going quadratically in the number of nodes. And in fact, it's a very simple exercise to extend this to an almost sure statement. With probability 1, the number of edges grows quadratically in the number of nodes. And in fact, there are 2 options. C could be either strictly positive, or it could be 0, in which case we get an empty graph. OK, so those are the only 2 options that are out there. And I'll just note that there's a little bit more intuition here. If you think of I'm at a particular node, and I say all these nodes are exchangeable, I'm saying all the other nodes kind of look the same to me. And so either I'm going to connect to some fraction of them, or I'm just not going to connect to them at all. OK, so this was, in some sense, known for a long time. So if you look back at all of those models that people were making of graphs, there were corrections that were involved to get away from this fact that we're getting these dense graphs, but they were corrections that change the distribution as we get more data. Peter Orbans and Dan Roy, in a review that came out in the archive in 2013, pointed out this issue, and there's been a lot of really excellent work that's been done to sort of address it recently. So some work by Cron and Fox in 2014. Victor Veitch, who is here, and Dan Roy have done some work on this, Borges and Chase. So I'm going to be just showing our approach to this, but I'll also encourage you to check out that other work. So what we've been thinking about, and this Crane and Dempsey work as well has been thinking about, is, well, gosh, this node exchangeability thing isn't working out. What else is there in graphs besides nodes? There's edges. So here's an alternative idea. What if we say that we're going to build up our graph sequence just as we did before, but now the fundamental unit, the thing that we add at each step, is an edge. So here on the first step, we add an edge. And since we're adding one edge at each step, we can again just label that edge by the step on which it's added. So here's the first edge. Here's the second edge. Here's the third edge. And the way that we're going to bring nodes in is we'll say that whenever a node is a part of an edge that's been instantiated, it will now be in the graph. So here we have 2 nodes. Here we bring in a new node, and so on. And the way that you can think about this is like emails again. Maybe these emails are coming in, and here one person has emailed another one. One of those 2 people emailed somebody else. 2 of the existing people we know about emailed, and so on. And we're getting more and more of these emails over time. In fact, we're getting 1 email at each step. And again, this goes off to infinity. Yes?
Are you actually going to maintain the temporal information? You're going to maintain the time information?
Right. So actually, basically the idea of exchangeability in this case, just like the idea of exchangeability in the node case, is that we don't think the time information matters. So in the node case, we're saying, oh, these people are joining Facebook, and we think that they could have joined in a different order. Here we're saying, oh, we have this collection of emails. Maybe we downloaded the Enron database, and we think that the order of the emails doesn't matter.
But there certainly are settings where the order is important.
Yes, absolutely. And this is true in any form of exchangeability. So you can imagine tons of cases where, for instance, in clustering, that actually your clusters are changing over time. Like, again, you're thinking about some corpus of documents in Nature, or literally any corpus, New York Times. The topics are fundamentally changing over time. But it's still useful to have these stationary models that don't change in time, because they can be a building block in the time-changing model. But here we're going to be thinking about stationary models. OK, so the assumption here that we're going to make, the exchangeability assumption, what we're going to call edge exchangeability, in contrast to node exchangeability, is to say I could take any step in the sequence out, look at its probability, and the probability shouldn't change if I happen to have seen these emails in a different order, if I happen to have seen these edges in a different order. And so the reason that we're going to talk about this at all is because it turns out, and we'll talk a little bit more about this theorem later, a wide class of edge exchangeable graph models do yield sparse graph sequences, unlike node exchangeable graph models, which can't with probability 1. OK, so in order to dig deeper into why this is, and to understand what's going on with this edge exchangeability in these graph models, we're going to end up talking a little bit more about clustering and learn about characterization theorems. So when we were talking about the Aldous-Hoover theorem just now, that was a really useful theorem, right? I mean, we were able to show once we had this Aldous-Hoover theorem, that all possible node exchangeable graph sequences yielded dense graphs or empty graphs with probability 1. And so it would be nice to have a similar characterization theorem for edge exchangeable graphs. Also, I've told you that we have this sparsity theorem. It would be nice to better understand what's letting us have this sparsity property. And so what we're going to do going forward is we're going to try to get this characterization theorem and get the sparsity theorem. And along the way, we're going to use results from clustering. OK, so remember we've been talking about clustering basically this whole time. It's been our motivating example. We have a bunch of data points, and we want to find the assignments of data points to clusters. And of course, we want typically these clusters to be meaningful. So we want to find, after we've done our clustering, that actually all of the data points, maybe these are all pictures, all of the data points in one cluster are actually pictures of cats, all of the data points in another cluster are pictures of dogs, et cetera. These were the parameters from earlier that the random measure was actually located at, each atom was located at. OK, so another way that we could represent an assignment of data points to clusters is in a matrix-like form. So here, pictures 1, 2, and 7 belong to a cluster. Pictures 3 and 5 belong to a cluster. Picture 4 belongs to a cluster. And the reason I say matrix-like rather than matrix is because there's actually no ordering on these columns. OK, well, the exchangeability assumption for clustering was that we think that if we exchange these pictures, if we downloaded all these pictures from the internet and we happen to have seen them in a different order, we don't think that that should change our distribution. Now, one of the things that's nice about this representation is that it's clear something's missing. What if I have a bunch of pictures, and in fact, some of those pictures have multiple animals in them? Or alternatively, what if I'm analyzing a bunch of documents, and my clusters are sports, arts, and economics? Well, if I'm talking about the movie Moneyball, clearly that has words about the arts, words about sports, words about economics, and so each data point should be able to belong to multiple groups. And so this is what Mike described earlier as a feature allocation, a generalization of clustering where each data point can belong to multiple groups or one group or no groups. In this case, the groups are called features instead of clusters. But again, we have the same exchangeability assumption. I downloaded these pictures from the internet, and I don't think that the order really matters. I think that if I'd seen them in a different order, I should have the same distribution over these features. And this is the way that we're able to get all of these processes that we were talking about, these gamma processes, these beta processes, et cetera. Yes?
Just clarification, what's this matrix? So picture 1 has both a cat and a sheep?
Yeah, so here we're saying exactly that picture 1 has a cat and a sheep in it, picture 6 has a lizard and a sheep, picture 7 has no animals.
And you're thinking of the features as being what, the columns?
Yeah, so the feature is essentially the group of data points that go together, but basically the column, yeah. So just as earlier, remember when Mike wrote out the partition and he said, oh, here's the set of data points that go together, 1, 2, and 5. Here's 9 and 8 go together. It's the same thing here. Only now those don't have to be a partition. They could have some data point that belongs to multiple groups. OK, so we can actually think of graphs as being a very specific subclass here. If these are the edges, edges have to belong to exactly 2 vertices. And so if we change to the specific case of a feature allocation, where each data point belongs to exactly 2 vertices, we get a graph. So here, the edges are going to be the rows. And we might want to think about the columns slightly differently. Rather than being a collection now, you could think of this as actually labels on people. So maybe these are the cat and the dog and the mouse are actually vertices, but more generally this could be Alice and Bob and Charles in a social network. And this is saying Alice and Derek communicated. OK, so in this case, we have exactly what we've been doing this whole time. The groups now, instead of being the clusters or the features, are the vertices. And exchangeability of the rows, which was very natural for pictures when we were talking about pictures, is now edge exchangeability. And so in fact, we can just generate the graph that would be generated by this matrix. So we could go to the first step. That's going to be an edge between 2 vertices. I'm just coloring them for ease of seeing where I'm getting this edge from. So it'll be between the red and the yellow vertex. Here we're going to have one between red and green. Here we'll have an edge between yellow and blue. And so on, and we keep introducing vertices as we see them. And you'll notice that we can have a multigraph here, that we can add an edge to a set of vertices that already have an edge between them, if we wanted to. OK, and we just keep building up this graph. And the edge exchangeability assumption is exactly the one we had before. If we exchange these rows, we don't think that it should matter. If we exchange emails, we don't think it should matter. Okay, so the basic idea here is going to be say, hey, this looks a lot like clustering. I mean, feature allocations were just a generalization of clustering. And now we see that graphs are a special case of feature allocations. And so if we know ways to characterize exchangeable clusterings, which in fact we do, maybe we can extend those to feature allocations and thereby to graphs. Okay, so let's think about what are the ways that we know. Well, one thing that Mike mentioned earlier is the idea of an exchangeable probability function. So in particular, if we have a clustering on n data points, and we know that the distribution over that clustering is exchangeable, that if I permuted these n data points, it wouldn't change anything, then it must be the case that there is some function, let's call it p, of the sizes of the clusters. So what's the size of the cluster? The size of the kth cluster is the number of data points in that cluster. So here it's 1. And it must be a symmetric function of the sizes of the clusters, because there's no ordering on the clusters. So we know that such a function p must exist. So this is called the exchangeable partition probability function when it exists. Mike gave us an example earlier for the Chinese restaurant process. But what I'm telling you now is that it's a much more general result. That if I have literally any exchangeable clustering, then I know that I can express its probability with an exchangeable partition probability function. So this is a result due to Pittman in 1995. Okay, so this is super useful. This is something that is used in things like Gibbs sampling. Certainly that's what the Chinese restaurant process, its main success story has been. And so if we have general clusterings beyond that, we can get new Gibbs samplers from something like this.
Sorry, what is SN1?
Right.
It's in latent?
So n is the number of data points, and SN1 is the number of data points in the first cluster. So here it's 3. There are 3 data points that belong to this cluster.
Just those.
So this is a symmetric function, so it actually doesn't matter which cluster I call the first. It's ultimately just a function of the sizes of the clusters. So if I say, OK, the sizes of the clusters here are, this one has 3, this has 2, this has 1, this has 1. So this will be a function of the set 3, 2, 1, 1, the unordered set.
So number of cat pictures with cats.
Yes, exactly. OK, so this is obviously much simpler than a lot of other representations. Yeah.
Every data is contained in just one cluster?
Yes, exactly. So for clustering, every data point must belong to exactly one cluster. But of course, we want to get beyond that. We want to say, oh, maybe data points could belong to multiple groups. And that will be the idea of a feature allocation. So we'll get to that immediately next. So here we're just saying, OK, every exchangeable clustering has an exchangeable partition probability function. This is a useful thing, not only for theory, but also for practice. And so maybe we might ask if feature allocations have this. Yeah?
Is that probability function defined for countable infinity of arguments? Like, how do you define p?
Yeah. So what it is it changes. It's actually a function of the unordered set of the number of clusters. And so there's not really sort of a fixed number of inputs that it takes. It actually takes the unordered set of the sizes of the clusters.
It depends also on its cardinality, right?
I'm not.
So n, if I change n.
Oh, yeah. So it changes with the cardinality. Yeah. OK, so another way that we could define this that would be perfectly equivalent is to say that it's a function of the number of data points and separately a symmetric function of the sizes of the clusters. Because the sizes of the clusters, if we add them up, give us the number of data points. So therefore, that is a symmetric function of the sizes of the clusters. This is just a boring thing to do because it's completely, it's just repeating what we already had over here. But it's actually necessary when we go to feature allocation. So now imagine that I have a feature allocation. Each data point can belong to multiple groups simultaneously. Each picture can have multiple animals in it. And now, if I make these the sizes of the features, so the number of data points in a feature, the number of pictures of cats, for instance, then I can define this as the exchangeable feature probability function. So all I'm saying at this point is I'm saying, oh, if I have the probability of a feature allocation, and it's a function of the number of data points and a symmetric function of the size of the features, I have an exchangeable feature probability function. Now I know I have to include n here, because it's no longer the case that the number of data points is a symmetric function of the sizes of the features. I could have 100 data points and 0 features. I could have 1,000 data points and 0 features. There's not this functional relationship anymore.
Sorry, the sum of these n1 through nk is not n?
Yes, so it does not have to be n. So for instance, I could have literally I could have everything be 0 so that there aren't even any s's. And then I could have n be anything. So it's not. OK, so in fact, as we'll see in a moment, we can show that it is not the case that every exchangeable feature allocation has an eFPF. So this doesn't characterize all the exchangeable feature allocations. But it is useful still for things like Gibbs sampling. And it's used in, so there's a generalization, or not a generalization, a version of the Chinese restaurant process that exists for feature allocations called the Indian buffet process, and it has one of these. OK, but nonetheless, this does tell us what we could define for vertices. We could say, OK, well, now let's imagine that, again, each of these rows is an edge, and each of these columns is a vertex, and so each edge belongs to exactly 2 vertices. That's exactly a feature allocation, where this is the size of the vertex, which, if you think about it, the number of edges that belong to a vertex, that's actually something we know. That's called the degree of a vertex. So in fact, if we're talking about vertices, we know that the number of edges is a function, a symmetric function of the degrees of the vertices. And so we can get rid of n again. And so we can define this as the exchangeable vertex probability function. And we have reason to hope, at least on the face of it, that it might be a way to characterize all edge exchangeable graphs, because we were able to get rid of n, and that kind of looked like clustering. But in fact, that's not the case, and we can see an immediate example of why. So does every edge exchangeable graph have an eVPF, just like every every exchangeable clustering has an ePPF? And the answer is no, and here's a simple counterexample. So imagine that I have 4 vertices now. Now I'm not imagining that the number of vertices is growing infinitely. I just have 4. And there's only 4 edges that I'm considering, and it's these 4. And they might repeat as many times as I want, but I'm only allowing these 4 edges. And I'll say that at each time step, I actually just choose the edge IID that appears. It's either this edge, the edge between blue vertex and green vertex with probability P1, or one of these other edges with the corresponding probabilities. These are 4 probabilities that sum up to 1, and they're all between 0 and 1. OK, so if I had an exchangeable vertex probability function, then these 2 graphs would have to have the same probability. Why? Because they both have 4 vertices of degree 1. And the exchangeable vertex probability function only depends on the degree of the vertices. OK, so can anybody tell me what the probability of this graph is?
P1 times P2.
It's P1 times P2, because we have this edge, and we know their probabilities, P1 and P2. Similarly, this probability is P3 times P4, because we have those 2 edges, and we just multiply their probabilities. I can easily choose P1 through P4 to be a probability distribution such that this equality does not hold. And so this is a counterexample, a case where I have a clearly edge exchangeable graph. I mean, they're just IID, but I don't have an eVPF. And in fact, because graphs are just a special case of features, this is also a proof that I don't always have eFPFs. OK, so if I wanted to characterize all of the edge exchangeable graphs that are out there, I have failed. And I need to go back to the drawing board and think about how could I characterize edge exchangeable graphs. OK, well, luckily, we know more things about characterizing clusters, and so we can apply that here. So here I'm just building up my Venn diagram. The things with eVPFs, the graphs with eVPFs, are not all of the edge exchangeable graphs, because that 4 vertex graph we just saw is out here. OK, well, here's another thing that we know about clustering. Let me tell you a way to generate exchangeable clusters that should look pretty familiar from what we've done earlier. Imagine I have the unit interval from 0 to 1. And I put down some random partition of the unit interval. So this one happens to have 6 subintervals. I could have any finite number of subintervals. I could have a countable infinity, as we've seen. These subintervals themselves could be random. So this could be a Dirichlet process. It could be a Pitman-Ure process. It could be all kinds of things, or the GEM, I should say. And now what I'm going to do is, independently from this partition, this potentially random partition, I'm going to build up my clustering by saying, for each data point, I'll put down a uniform random variable between 0 and 1. So I'll do this IID for each of my data points, and I'll say that when 2 of these IID uniform random variables fall into the same subinterval, they belong to the same cluster. So 1 and 2 belong to the same cluster. 3 starts a new cluster. 4 starts a new cluster. 5 belongs with 3, and so on. Now, again, it's clear like we were talking about earlier, that this generates an exchangeable clustering. If I permute any two of these IID uniform random variables, I'm not changing the distribution of the clustering. And each one of them corresponds to a data point. And the awesome thing that Kingman showed in 1978, the harder direction, is that the converse is true. If I have any exchangeable clustering, then I must have this representation, known as a Kingman paint box representation, for its distribution. And in fact, one example of this is the Dirichlet process, but there are many other examples. Okay, why is it called the Kingman paint box? Well, you can imagine that there's some color associated with each of these subintervals, and when I put down my data points, they get colored with that color. But in fact, you could think of this color not just as some fanciful idea, but in fact as that parameter that we saw in the random measure, the parameter that describes how to actually generate data points in that cluster. So this would be something that maybe tells us how to generate pictures of cats, something that tells us how to generate pictures of dogs, et cetera. Now, I'm going to draw the exact same model, but slightly differently. All I've done is I've separated out each subinterval onto its own level. So here, I'm saying that I put down my IID uniform random variables, and each data point belongs to all the groups that it intersects. And it intersects one and only one group because these are mutually exclusive and exhaustive subintervals by construction. But of course, I didn't need to do that. I could have more general subsets. And so in fact, when I choose more general subsets, now when I put down my IID uniform random variable, it's going to potentially belong to multiple of them, and so I'm going to get features. So again, we can play the same game. We put down our IID uniform random variables independent of this potentially random feature allocation. So this data point belongs to 2 features. This data point belongs to no features, which is totally fine, because that's allowed in feature allocations. This data point shares a feature with the first data point, and so on. And again, it's straightforward to see that this has to generate an exchangeable feature allocation, because if I permute any two of these IID uniform random variables, I'm not changing the distribution of the feature allocation. And what we're able to show is that the converse is true. That if I have any exchangeable feature allocation, then there must be a feature paint box representation. Yeah?
So in order to show the converse, you're showing the definite or what the...
Yeah, these are basically the Di-Finetti mixing measures that we've been describing. So the Di-Finetti mixing measure for clustering is exactly the Kingman paint box representation. The Di-Finetti mixing measure for feature allocations is this feature paint box representation.
So
Yeah.
that kind of just says that it should exist, but you're saying here's the explicit representation.
I'm sorry, could you repeat the question?
The theorem, Di-Finetti theorem says that it should exist.
Right.
But you're saying here's the explicit.
Yeah, exactly. And so here's the key point. Di-Finetti's theorem doesn't tell you much that is useful necessarily. It tells you there has to be this Di-Finetti mixing measure, but doesn't necessarily tell you how to find it, that it has a nice form, anything like this. And we're saying, oh, in these particular cases, it does have a nice form. It's something that's actually quite usable. It corresponds to things that we've seen. In particular, in clustering, we just saw, hey, that looks a lot like the Dirichlet process. That's a particular example. And so we're saying, here's a particular sort of maybe easy to understand form of the Di-Finetti mixing measure. Let's nail it down. Yeah.
So if you specialize this to the graph case, so it still tells you the same thing, but the paint boxes have to, you can't have one vertex in three.
Exactly.
In 3 paint boxes,
Right.
So you have to enforce some constraints. So how do you do that?
Yeah. Basically by just saying those constraints are enforced. So you exactly anticipated the next slide. Let me say something really briefly before we're going there. So this is basically the whole picture. There's technically something that I'm not telling you about, which is dust. So in the clustering case, dust is basically a data point belongs to a cluster and you never see that cluster again. And so there's a similar conception of dust here as well. And we can also characterize that, which we've done in a recent paper for this feature allocation case. OK, so the graphs case, basically you've just completely solved it, which is to say, oh gosh, we need to make sure that in each one of these slices, we have 2 nodes. And that's it. We're going to get an edge exchangeable graph by doing that. We're going to say, OK, for each one of these data points, we put down a uniform random variable. If we put the constraint that each slice has 2 nodes, then now each data point belongs to 2 nodes. Each edge belongs to 2 nodes, because now our data point's an edge. Yeah.
How do you generate that as a stochastic process?
Right. So the question in all of these cases, and it's really not just the graph case, it's the feature case, it's the cluster case, although more so in the feature and graph case, is how do you actually generate a usable form of this? And so in a moment, I'll talk about, here are some particular processes that we use. But they're basically typically independence assumptions that we use. So if you think about the completely random measures we talked about before, the reason that those are nicer and the reason that we use them in practice is because they have certain independence assumptions that make it easier to specify the model and easier to do inference. And so even when you talk about completely random measures, we talked about there's that further independence assumption that the rate measure factorizes. We don't need that, but it's easy to use. And so that's what people actually do in practice for things like features. What is likely to happen with things in this area is that we would say that we get an independence assumption. I'll describe what a really natural one is in a second. OK, but let's just walk through this idea for the moment. So here, we just do the obvious thing. We keep putting down these IID uniform random variables. We say, oh gosh, each one of these generates an edge. So clearly, if I permuted them, these IID uniform random variables, I'm not changing the distribution of the graph. And likewise, they correspond to edges, so I'm getting an edge exchangeable graph. So it's this sort of immediate corollary that an edge exchangeable graph must have this, what we might now call a graph paint box. And in fact, actually, sometime the case that you were describing, where a data point and edge can belong to multiple vertices, is of interest. And so that would be a hypergraph. And so that's just the extension to the feature paint box. Similarly, we can get self-edges by saying that it's OK for a data point to belong to one feature. Or if a data point belongs to no features, we can think of that as a skip. Maybe in this time period, somebody didn't send an email. Okay.
What if you don't want repeated edges?
Oh, so if you don't want repeated edges, then this is not the model for you. So there are two options. So one is, don't use this, because you're definitely going to get repeated edges. And in fact, one thing that we can see is that you're going to get an infinite number of repeated edges. So you can imagine, maybe that's reasonable for you sending emails with your family, but maybe that's not reasonable in some other cases. Now, there's 2 points I want to make. So there's actually, I'd mentioned this idea of dust. So there's actually also dust edges here. So dust edges are, the Nigerian scammer sends you an email and you never hear from them again. That can happen. 2 people who have never communicated before can communicate once, and that can happen. But in general, unless you do something like take your multigraph and switch it down to a single edge, this isn't going to be representing that. And so you can think of this, I think, as if you have something like relational event data, something where this is natural, this could be a good idea. But in cases where you don't, it's not going to be a good idea. But it's also worth thinking about if you are only having binary edges, what's the nature of your graph growth? And how is that happening? Because this is fundamentally about growing graphs. But yeah.
But I mean, is there exchangeable models if you don't have?
You can't have edge exchangeability without allowing. OK, well, so the technicality on that is dust. You can have dust. But then nothing's ever going to connect to anything else. So you can't have edge exchangeability and have vertices keep connecting to each other. And that's what this theorem is showing. So it's worth thinking about, and I think it's an open, interesting question. Is there another form, an interesting form of exchangeability that expresses some natural assumption that would allow you to do that?
I mean, there is, clearly, right? Like the model that Dan and I have does exactly that.
But yours also does repeated edges. I mean, the Cronin-Fox in your model. Well, let's maybe talk about this later.
Okay. It definitely doesn't. When you've seen 2 vertices, you know everything that happens between those 2 vertices, often to like the
Right, with the alpha growth model. OK, yeah, so this does have this property as long as you have the right likelihood function. Yeah, OK, fair enough, great, cool.
So that is exchangeable and.
So this is a different type of exchangeability. So Kallenberg exchangeability, which is described in Cronin-Fox and the Veitch and Roy paper, is, so remember our random measure from before, we'd say that we think that the probability of, or the measure applied to these 2 sets, those could be exchanged. So it's fundamentally something about sort of the labels here at the edges, or sorry, at the vertices.
Oh, so they have a different definition of it.
It's a different definition of exchangeability. So this is a very open area right now, and it's been a lot of work in this area. And so I definitely encourage you to check out those papers that I listed on the earlier slide. OK, cool. So in this case, we do in fact have a characterization theorem for edge exchangeable graphs. And it is this graph paint box.
Mara,
Yeah.
so this will not work also in the case of finite number of nodes, no?
Right, so everything we're talking about here is in the growing number of nodes, but that's because we define density and sparsity in that case. So you can actually get a finite number of nodes and have edge exchangeability. It's just that we weren't really talking about density and sparsity there because it depends, the definition depends on the growing number of nodes. But you can have edge exchangeability and a finite number of nodes.
But can you have a EV prior on them? No.
No, so the BNP aspect is fundamentally the growing aspect. And so it's sort of like having a Dirichlet distribution versus a Dirichlet process. I mean, you can have the Dirichlet distribution just like you can have, as an example, the Kingman paint box, but you won't get the BNP aspect. Yeah. Okay, so let's talk about how we can get sparsity in this case. Well, remember, okay, as we were just saying, if we actually want to get this growth, we need the number of nodes to go to infinity. And so we've seen from the very first lecture that in that case we need a countable infinity of latent nodes. So let's instantiate those. And the particular type of independence that we might assume here to get a simpler model than the full graph paint box is we might say that we essentially draw one of these processes that we've seen. A Dirichlet process, a gamma process, a beta process. We draw some rate for each vertex I. So this is just like you can imagine, maybe these rates are coming from a beta process, from a Dirichlet process, from gamma process, and we draw an infinity of them in one of those ways. And then we draw the edge between I and j with probability proportional to wi times wj. So we're making a strong independence assumption here, but it's a particularly easy model to use in practice. So if we do that, this is a particular form of the graph paint box where we know that each subset has probability, has total mass proportional to the wi. And we know that they have to intersect in a particular way. In particular, the intersection of two of these has to be equal to wi times wj or w1 times w2 in this case. Okay, so basically if we make some assumptions on those w's, then we're going to get what we want. So we're going to choose our w's from some Poisson point process with appropriate tails. So in particular, all we're saying here is that the tails decay like a power law, and there might be some variation around that according to what's known as a slowly varying function. And so this encompasses basically a lot of the power law versions of the processes we've already seen, gamma processes, beta processes, and so on. So it's a very rich class of basically completely random measures. And if we do that, we can show that the number of vertices grows almost surely like a power law. The number of edges grows almost surely linearly. And so long as alpha is between 1/2 and 1, this will be exactly the subquadratic growth that we wanted. And if we do this thing where we say, let's just have binary edges by squishing down our multigraph, we can get, in fact, any form of alpha will give us this power law growth. Okay, so we have this wide class of edge exchangeable graph models and sparse graph sequences. Okay, I'll just skip ahead here. We get some empirics as well. Okay, so at this point we did what we set out to do. We wanted to get this theorem for characterizing edge exchangeable graphs. We wanted to get that sparsity exists in edge exchangeable graphs, but it remains to sort of fill out this Venn diagram that we've created. Where does sparsity fit in here? Where do graph frequency models fit in here? Well, let's start with graph frequency models because we know that some subset of them are sparse. And in fact, you can think about it pretty easily that graph frequency models are going to have to be a strict subset of these because they impose a very strong independence assumption. In fact, an example of something that's not a graph frequency model is our 4-vertex model from earlier. And at that point, you get to thinking, okay, well, the 4-vertex model isn't a graph frequency model. The 4-vertex model doesn't have an EVPF, this vertex probability function. And in fact, we can show that those two things are the same. So in fact, the exchangeable vertex probability functions are the same as the models with graph frequency models. And this actually comes from essentially an existing result on feature allocations that we have from earlier. Likewise, we can show that not only do we know some of these are sparse, but some of the other edge exchangeable models are sparse as well. And I talked to you about this idea of dust already. Okay, so there's a lot to remain to do. So, we talked there about there being some sparse edge exchangeable graphs, but we made this independence assumption that made it quite easy. What are all the sparse edge exchangeable graphs? We could probably do this with our characterization theorem. This isn't the only type of power law that's interesting. We want to get that the number of triangles can grow as a certain power of the number of vertices, or at least have a particular growth rate, that the degree distributions have a power law. So there are a lot of other interesting things, and it remains to be seen whether that's true. And what's nice about these types of characterizations, this clustering Di-Finetti theorem, the feature allocations, and so on, is they lead us to think about natural models, inference that we can have, how can we extend beyond what we already do, and so it's natural to do that next. Okay, so what we've seen so far in this series of lectures, is hopefully a motivation for why we're even looking at non-parametric Bayes. We started off by talking about clustering and Dirichlet processes and how we can get this growing number of clusters. And hopefully something that's become clear is that it's not just the Dirichlet process that's out there. There's a lot of other processes that we can get with a lot of other potentially desirable behaviors. And we also get a lot of different representations of these processes. So with the Dirichlet process, the Chinese restaurant process is useful if you're looking for something like Gibbs sampling. But the Dirichlet process itself is useful if you're looking for something like, we actually wanted to be able to use variational Bayes or Hamiltonian Monte Carlo. We wanted to take advantage of distributed computing, things like that. So these different representations are really useful from an algorithmic standpoint as well. And then hopefully, at the end here, you've gotten a sense of, in fact, there's a lot of different types of data that are out there that are really only just beginning to be explored. So certainly trees and clusters and features, these things have been looked at for a while now. But how can we get beyond that to good models for graph data, for all of the sort of rich connected data that we have? Thank you. Yeah.
So I'm trying to still get a sense for what exchangeable graphs are like. So like the email graph, right? So your theorem is saying that there is some one-dimensional space, the paint box space.
Well, it's not. I guess I wouldn't say it's exactly one-dimensional because you have sort of each node has its own subset going on, and so you have to specify the node subsets.
The node subset.
Yeah.
Right. On that line.
Or yeah, in general, yeah. It's enough to look at the unit interval in all of these cases.
So what does that say? I mean, intuitively, like every person has some kind of a partition of the unit interval which corresponds to some feature? Or?
Yeah, or maybe every combination of people has some probability that something happens between them or something like that.
So that's exactly what I'm trying to get at. So
Yeah.
what's the sort of ground truth? That's what I'm trying to understand.
I'm not sure what you mean by ground truth.
Like, how should I think of it? So yeah, there's a group of people. Yeah, so I just want to, yeah.
Yeah. Right. I think fundamentally the clustering case is probably the easiest. So what you're saying is if you have exchangeable clustering, then you must have some probability essentially that's associated with every cluster. And so all you're doing is generalizing that in the feature allocation and graph case. You're saying, okay, now instead of just some partition, some probability, some strict probability, now you have the general probability of a feature, but also the way that it interacts with other features. Now you have the general probability of a node, but also the way that it interacts with other nodes.
So other ways of doing it would have been some kind of, I don't know, pairwise process like Eating model or something? Or?
I mean, well, there are many other ways that you could generate graphs. They wouldn't be exchangeable unless they had, or this particular form of exchangeable unless they had this representation.
So if we think that emails indeed don't,
Yeah, so this is true for all of this. So I mean, same thing with clustering again. You're making this exchangeability assumption. If you think that it's not warranted, then you're not going to need to use these models. It comes back to, I think, something like this independence assumption. It's usually a simplifying assumption, and these simplifying assumptions get us down to usable models. And the question is, we just want to make sure we understand those assumptions going in to understand sort of whether they're correct or not, or how off they are. And also, what's nice about these representations, in particular these Di-Finetti mixing measures, is that they're able to tell us things about all of these models at once. And so I think what was really powerful about what we saw about node exchangeable graphs is that we were able to say in one fall sweep that if you ever make any node exchangeable graph model, it could be one you've never even made before, we know it's going to generate dense graphs. And so that tells you, oh gosh, if I'm trying not to get dense graphs, then I need to step away from this type of generating framework even. I need to not make a model that even has this property. I need to make sure that I'm out somewhere else. Yeah.
Can this construction accommodate community structure?
Yeah. Yes, it can. So for instance, you could do it via this sort of vertex popularity model idea, which is one that has been used for a while in other frameworks as well. But just by the way that you're organizing the communities, but you could also do it within the graph paint box itself.
So I don't see how exchangeability will hold in that case. So if you take vertices in this community and vertices in this community, they're clearly not exchangeable. You can't just exchange them and keep the same problem.
Let's maybe talk more offline about that one. Yeah.
So for vertex exchangeable graphs, you're going to get the dense property. Can you do any kind of analysis and say something like, oh, only certain subsets of the vertices are exchangeable?
Right. Oh, so I think there's been some interesting work that Bailey Fosdick and others have been doing where they say, oh, yeah, actually, maybe we only really want exchangeability within communities or things like that. And so then you're able to get away from this sparse assumption, and that seems to be pretty productive. Yeah.
So have you taken any of your generative models and looked at, see if they can actually model real graphs in real life?
Right. So there's different levels here. So one is, can we simulate from these and get the desirable behaviors? And the other one is, are we going to actually put together the models on this? And so I would say that in general, this area is so new that we're just starting to see in sort of any of these alternative forms of exchangeability, we're just starting to see those actual models being used on data. And I think in the next few years, we'll see more of that. But in this case, it's...
Well, actually, I just mean like go out and measure the connectivity of the internet in some sense and then see if you can actually model that.
Oh, right. Okay, so I think that's what I was getting at in those sort of final bullet points, that there are a lot of other things that you're interested in beyond this particular sparsity property, that there's actually, you look at degree distributions, you care about triangles and so on.
Yeah. So, but what we're really interested if it actually can model something out there that...
Well, yeah, but what does that mean if it actually can model, right? Usually there's something that we're actually interested in getting from it, and we want to know, can we get that? And so we have to specify.
The simplest example, I guess the basic question is if you've taken this model and actually verified it against real data or something.
But I guess what I'm saying is, what does verify against real data mean? So there are a lot of things that we can do with real data. We could try to find communities, we could try to predict links, we could do et cetera. And so, in this case, this is just a framework right now. We haven't started those things, but I think you want to ask the specific question of which one of those are you doing too.
So just do the basic things. Like it has the right number of edges, or the connectivity is correct, or the degrees are right, or whatever. It's pretty simple.
So, but then I'm not understanding what you're saying. So usually what we would do in this case, we would build up our generative model, as we said, and then we would go and find the posterior on our parameters given our data, and we'd want to check that against something. We want to say, oh, are we getting this parameter right, or something like that. I mean, we could just simulate from this and see, what that simulation looks like, but it's not necessarily going to look like any particular graph, and that doesn't necessarily have to bother us in that case.
But you might try to simulate and get the properties of existing graphs, right?
Sure, I think this comes back to my bullets here. Maybe we can talk a little bit more offline. Yeah.
So one of the cases, I don't know if you mentioned it before, it will be like email communities and change over time, no? Because there could be users you have
Yeah.
members before.
Yeah. So this comes back to the point that I was making that.
Line inference are the natural, no?
So I think you're getting at this point that I was making before, that I think these stationary models can be part of it's like a tool or a part of a broader model that's actually non-stationary and changing over time. And so here we're focusing on the stationary aspect, but for instance, the Dirichlet process in clustering has been used for very non-stationary models, but it's sort of a step in those. So it's like you can have a Dirichlet process, for instance, with
I think that you have to think on the non-stationary model to provide the validation that there could be some object that you haven't observed, and that could validate the infinite number of know.
Right, okay, no, but so there's different types of.
To validate the non-parametric model, and then to use the.
Well, but there's different types of new things that you could observe, right? So you could observe new things because you haven't seen them yet, and maybe they were relatively rare, and that's what's going on within a Dirichlet process. You could observe new things because fundamentally you have a non-stationary process and things are changing, and that's not what's going on in a Dirichlet process. And there you need a model that actually changes over time. Yeah. Yeah.
Just a comment about the question about multiple edges. You can create simple graphs by running your graph paint box process and just conditioning on that process doesn't create multiple edges. And that gives an exchangeable graph.
Yeah, you lose the exchangeability. Yeah. Great. Yes?
I think it's related to a question that other people have asked, but there's something of an art, it seems to me, in picking the right model.
Yeah.
So I'm wondering, if you could give some insights into that. What is the desiderata, and do we have any understanding of how much that affects what's going to happen downstream? If this is used as a component in something where you're doing some inference or learning or whatever,
Right.
how much does the choice of model actually matter?
Right. I mean, to a certain extent, I think what you want to do in all of these cases is sort of check that what you're doing is giving you reasonable results, actually empirically. So there are various things you can do. I mean, if you have some sort of actually like a classification or regression task, then there's a very clear way to actually evaluate that at the end of the day. There are some nice things like posterior predictive checks that you can do that actually make sure that the models that you're using in some sense are capturing the right aspects of your data and that you're not totally off in building your model and that it's it really isn't looking like what the data is looking like. So there are some checking mechanisms that can be done. I mean, fundamentally, not just in these cases, but in any case where you're building up a likelihood, you're making these choices. You have fundamentally this George Box quote: "All models are wrong, but some are useful." And so you want to be identifying those useful ones. And so in particular, I think one thing that helps is to be able to say, oh, here's some desiderata. Does our model actually capture that? And that's what we're getting at with these things like, the Dirichlet process is nice. It gives us these nice empirical results until we realize that in, for example, text applications, we know that we have these laws that are power laws that, for instance, the number of different types of words grows as a power of the number of tokens, the sort of individual words in a corpus. And so if we're not capturing that, then we know that we're getting something wrong. Or if we're finding that we want to find these clusters and then we're not finding the right number of clusters, we're always massively underestimating them, then we know that we want to go back to the drawing board and create a new model in that case. Yeah.
Can you generate small world type graphs with this framework?
I don't know. I'd be interested to talk to you after about that. Yeah.
Is estimating posteriors using anything like Gibbs sampling or ratio inference or whatever somehow comparatively harder for the non-parametric ones compared to the parametric ones? Or?
Right. So I mean, there's definitely going to be an aspect certainly of just you're trying to get some growth aspect, or you're trying to learn this extra dimension almost, as it were, this sort of streaming dimension. We're getting more data, and so I mean, there's some sense in which it has to be harder just because there's somehow this extra parameter. But fundamentally, a lot of the work that's been done, especially recently, sort of reduces to the parametric case. So the idea of truncation, for instance, is to say, I have this infinite model that I want to use, and I'm going to approximate it with a finite model. And so as long as, again, a point that I was making earlier, that truncation error is on the order of the approximation error that I'm getting from my Markov chain Monte Carlo, my variational Bayes, then I haven't lost anything. But then I have to quantify that truncation error. I have to understand what's going on with that. I have to think about what's a correct truncation to be using that still captures that model. And so that's an extra bit of work. But in terms of actually the speed of these algorithms and things like that, it's not going to be worse than having that same number of parameters, at least for that set of data.